Dobar dan svima. Otvaram javnu govornu doktorskog rada pod naslovom Surface Modification and Implementation of Natural Zeolite into Innovative ili površinska modifikacija i funkcionalizacija prirodnog zeolita klinovita, koji je izradila Barbara Kalebic, magistar inženjerka ekoinženjerstva u okviru međunarodnog vojnog doktorata na projektu Kraljevo 2020 Novac. Doktorat je uređen na Tehnološkom i Tehnološkom fakultetu i Univerzitetu u Belgradu i Fakultetu za avijacijsko i brodogradnje sveučilišta u Zagrebu. Pošto imamo i publiku sa projekta Novac, također će i odgovor biti na engleskom, samo ću reći par reči na engleskom vremenu. So I welcome the people following us on YouTube. So this is the public oral defense dissertation, named Certification and Consolidation of Natural Zeolite by the candidate Barbara Kalebic. So the next sentence will not be in English because this is formal part which we need to follow according to the University of Belgrade. So after that, our candidate Barbara, she will present her defense thesis in English. Dakle, nastavljamo na čitanje formalnog dela. Barbara Kalebic, bila je indeksar 35. Napisala je doktorske akademske studije školske 2019-2020 godine, studijski program inženjerstva i zaštite životne sredine na Tehnološkom fakultetu u Beogradu. Nakon svih polaganja ispita prijavila je temu doktorske disertacije baš u 6.2021. godine odlukama nastavnog naučnog veća Tehnološko-metaloškog fakulteta i veći naučnih oblasti tehničkih nauka u Fakultetu u Beogradu tokom 2021. godine. Za mentora je imenovana profesorka dr. Nevenka Rajić. Također je odlukama nastavnog naučnog veća Tehnološko-metaloškog fakulteta i veća naučnih oblasti tehničkih nauka za drugog mentora je imenovana profesorka dr. Kalebic, redovni profesor sveučilišta u Zagrebu, Fakultet za strojarstvo i brodogradnju. 29.6.2021. godine nastavno naučno veće Tehnološko-metaloškog fakulteta imenovalo je komisiju za ocenu naučnih sastavnosti teme doktorske disertacije Barbara Kalebic u sastavu dr. Nevenka Rajić, redovni profesor Univerziteta u Beogradu, dr. Dragan Kavrenović, redovni profesor Univerziteta u Beogradu, dr. Vladimir Pavićević, vanredni profesor Univerziteta u Beogradu, svi sa Tehnološko-metaloškog fakulteta, dr. Nikola Škorović, naučni savjetnik Instituta za fiziku Univerzitetu u Beogradu i dr. Jelena Pavlović, naučni savjetnik Inovacionog centra Tehnološko-metaloškog fakultetu Univerziteta u Beogradu. Na sednici nastavnog naučnog veća Tehnološko-metaloškog fakulteta usvojen je izveštaj o komisiji o podobnosti teme, koje je već naučnih oblasti tehničkih nauka Univerziteta u Beogradu usvojilo 31.8.2020. Prve čime je Barbara Kalebic odobrena izrada doktorske disertacije pod nazivom Površinska modifikacija i funkcionalizacija prirodnog zeolita klinovita. I u paraleli Fakultetsko vijeće Fakulteta strojarstva i brodogradnje sveučilišta u Zagrebu odobrilo je tehničku temu disertacije pod naslovom i za mentorke također odredilo profesorku dr. Nevenke Rajić sa Univerzitetom u Beogradu i profesor dr. Lidović Đurković sa sveučilišta u Zagrebu. Nakon podnošenja uređene doktorske disertacije nastavno naučno veće Tehnološko-metaloškog fakulteta 11.5.2023. godine imenovalo je komisiju za ocenu doktorske disertacije također fakultetsko vijeće fakulteta strojarstva i brodogradnje u sveučilištu u Zagrebu ima svoju redovnu sednicu održanu 23.5.2023. godine je imenovalo, odnosno potvrdilo komisiju za ocjenu doktorskog rada. Sa ove strane u komisiju su imenovani dr. Maja Đolić, docent Univerziteta u Belgradu, Tehnološki metalurški fakultet, dr. Davor Ljubas, redovni profesor u Zagrebu, fakultet strojarstva i brodogradnje, i dr. Nataša Novak-Tušar, redovni profesor Univerziteta u Gorici, fakulteta za znanosti i Evrope. Nakon što je komisija za ocjenu podnela izveštaj u uređenoj doktorskoj disertaciji i isteka rok od 30 dana na uvidu javnosti disertacije i izveštaja, Nastavno naučno vijeće Tehnološko-metalurškog fakulteta 24.8.2023. godine donelo je odluku o prihvatanju izveštaja o uređenoj doktorskoj disertaciji i odluku o imenovanju komisije za odbranu doktorske disertacije. Gore imenova komisija je dostavila pozitivnu ocenu doktorskog rada i fakultetskom vijeću fakulteta strojarstva i brodogradnje sveučilišta u Zagrebu, koje je ovu ocenu prihvatilo i takođe imenovalo komisiju za odbranu doktorskog rada. Dakle, komisija za odbranu doktorske disertacije, koju imamo danas ovde, je u sastavu dr. Nikola Škoro, viši naučni saradnik Univerziteta u Beogradu, institut za fiziku, dr. Maja Đolić, docent Univerziteta u Beogradu, Tehnološki metalurški fakultet, dr. Vladimir Pavićević, vanredni profesor Univerziteta u Beogradu, Tehnološki metalurški fakultet, dr. Davor Ljubas, redovni profesor sveučilišta u Zagrebu, fakultet strojarstva i brodogradnje, dr. Hrvoje Cajner, redovni profesor sveučilišta u Zagrebu, fakultet strojarstva i brodogradnje, dr. Milko Mandić, vanredni profesor sveučilišta u Zagrebu, fakultet kemijskog inženjerstva i tehnologije, i dr. Nataša Novak-Tušar, redovni profesor Univerziteta u Novoj Gorici, fakulteta za znanosti i tehnologije. Za predsjednika komisije imenovan je dr. Nikola Škoro, viši naučni saradnik. 11.9.2023. godine veće naučnih oblasti tehničkih nauka u Univerzitetu u Beogradu donelo je odluku kojom se daje saglasnost na izveštaj o uređenoj doktorskoj disertaciji Barbare Kalebic pod pomenutim nazivom, čime su se stekli zakonom propisani uslovi da se doktorantkinja pozove na javnu odbranu doktorske disertacije. Takođe, fakultetsko vijeće fakulteta strojarstva i brodogradnje sveučilišta u Zagrebu je potvrdilo predloženi termin za javnu usmenu odbranu na Tehnološkom metalurškom fakultetu Univerziteta u Belgradu. Sad ću pročitati kratku biografiju. Znači, Barbara Kalebic je rođena 1924. godine u Zagrebu, gde je završila osnovnu i srednju školu, diplomirala je 2018. godine na fakultetu kemijskog inženjerstva i tehnologije, sveučilišta u Zagrebu sa temom na studentskom programu ekoinženjerstva. Osnovni master rad radila je na temu inovativnih metoda pročišćavanja vode s ciljem uklanjanja novih vrsta kontaminanata iz vodenog medija s fokusom na fotoprofilitičkoj degradaciji hormona estrogena i mineralizaciji salicilne kiseline ozonizacijom. Mentor je bio profesor Dr. Kalebic. Tehnološki metalurški fakultet Univerziteta u Beogradu, doktorski studijski program inženjerstva zaštite životne sredine i fakultet strojarstva i brodogradnje sveučilišta u Zagrebu, doktorski studij inženjerstva materijala, upisala je školske 2019-2020 pod dvojnim mentorstvom profesorke Rajić i profesorke Đurković. Dakle, doktorat i zaposlenje na Tehnološkom metalurškom fakultetu Univerziteta u Beogradu kao istraživački pripravnik je bilo u okviru evropskog projekta Novelties. U toku svog rada Barbara Kalebic je objavila i autor je 3 štampana rada na naučnim časopisima i međunarodnog značaja i 5 saopštenja na međunarodnim konferencijama iz oblasti istraživanja, iz koje je predložena tema doktorske disertacije, objavljene 2 rada u vrhunskim međunarodnim časopisima i 1 rad u istaknutom međunarodnom časopisu. 2021. godine dodeljena je nagrada za najbolji poster na PhD 2021 direktorove konferencije. I sada ćemo preći na odbranu. I will now switch to English. So please, Barbara, give us a presentation of your doctoral thesis in hopefully less than 45 minutes. And then we will continue.
Evo, prvo jedno hvala na hrvatsko izmenje i hvala doktore Šporo na uvodu. Sad ću ja reći na engleski. So thank you all for coming and tuning in over the internet. So since you already heard almost everything about me, I will start with my presentation. So the presentation is organized into 4 main sections, starting with the order of context of my research, followed by the experimental part, analysis of the results, and finish it with the conclusion. So let's start the introduction and the motivation for this research. The constant growth of the world population resulted in the increased demands for high living standards, which, among others, include access to clean and portable water. These demands have led to widespread use of various chemicals, many of which become contaminants entering the environment. The limited availability of fresh water sources, accounting for less than 2% of the Earth's total water, combined with their uneven distribution, and the fact that almost 30% of the global population lacks access to safe fresh water, highlights the importance of smart water management. So over the past few decades, the consumption of different novel chemicals has significantly increased. Many of these chemicals are contaminants classified as organic micropollutants. Although their concentration in the environment are still low, the negative effect on water organisms has already been observed. And the OMPs can easily enter the water environment through different pathways, as it's shown in the figure on the right. So despite saving 1 million lives, the uncontrolled consumption of antibiotic for medical purposes, but as well as in livestock production, poses a significant threat to water environment. Due to the structural complexity of antibiotic molecules, they are stable and thus resistant in the environment. They are extremely toxic to water organisms and induce development of antibiotic-resistant bacteria. So in 2014, this phenomenon was recognized as one of the top 10 global public health concerns, with an antibiotic-resistant disease predicted to claim up to 10 million lives per year by 2050. So in this research, the antibiotic ciprofloxacin was used as a model pollutant. It is on the European watch list from 2018, a list established to monitor the concentrations of contaminants of emerging concern in the water of European Union. Ciprofloxacin is widely applied fluoroquinolone antibiotics for treatment of different bacterial infection, and since due to its extensive use, it's present in the surface water in a wide range of concentrations that can be even 50 milligrams per liter near drug manufacturing plants. Also, antibiotic molecules have a switterionic nature, which means that the molecule charge strongly depends on the pH of the solution, as it's shown on the figure below. So since TIP, as other antibiotics, cannot be completely removed from water by conventional wastewater treatment processes, different advanced processes have been investigated for its removal. Among these processes, absorption stands out as a promising approach, since it proved to be efficient in removal of non-biodegradable pollutants present in low concentration and can use a wide range of adsorbent material. So the most abundant natural zeolite, clinoptilolite, has been extensively studied for removal of different species, inorganic and organic, from water media. Due to its unique structural features, it has a wide range of applications, so from catalysis and ion exchange to adsorption. And the most common mechanism of organic species removal on clinoptilolite include electrostatic interaction and ion exchange reaction. According to literature data, cyprofloxacin was already removal from water was already investigated on different adsorbents material, also clinoptilolite, and it showed a good potential for the cyprofloxacin removal. Here, it is important to point out that the removal adsorption efficiency were obtained at different experimental conditions, of course. So, in addition, the clinoptilolite adsorption ability can be improved by different modifications, physical or chemical modifications, and then they can improve specific surface area or pore volume, or alter the surface charge and structure of clinoptilolite. So the reusability of the adsorbents can significantly reduce the process costs. So the clinoptilolite regeneration is mainly based on the desorption of the adsorbent, the reverse ion exchange reaction, or the adsorbent degradation. Since the commonly used conventional method have some disadvantages in terms of energy efficiency and performance, the non-thermal plasma treatment in this research was investigated as an innovative and novel method for clinoptilolite regeneration. In general, plasma is partially or fully ionized gas, which contain a neutral and excited species, ions, electrons, photons, etc., that have enough energy to promote different chemical reactions. So plasma can be divided into thermal and non-thermal plasma according to the temperature of the species that are present in the plasma discharge. And the non-thermal plasma operating at atmospheric pressure was of interest in this research. So far, plasma was used for surface activation and modifications of different adsorbent material, including zeolites, as well as for surface cleaning. So I will continue with the experimental part, just in brief. It contained of 3 parts. First, the adsorbent preparations and their detailed characterization, then the adsorption study and the spent adsorption study, including leaching test, antibacterial activity test, and finally the regeneration of spent adsorbents. So the clinoptilolite-rich zeolitic tuff from Serbian deposit Slanci was used as a starting material. According to the quantitative analysis, the zeolitic tuff had a high content of clinoptilolite and feldspar and quartz as a satellite phases. Also, the clinoptilolite has relatively high cation exchange capacity, and the used particle size range was up to 125 microns. First, the magnetic clinoptilolite was prepared by 2 different approaches, the standard co-precipitation method and the microwave-assisted method. Then, subsequently, the magnetic clinoptilolite obtained by microwave-assisted method was coated with graphene oxide using ultrasound treatment. So the adsorption experiments were performed by batch method at different initial cyprofloxacin concentrations and temperature. The cyprofloxacin concentration infiltrate after the adsorption was measured by the UV spectrophotometer. The analysis was statistically analyzed using the central composite design to obtain the optimal condition of the cyprofloxacin adsorption of each of these adsorbents, and the use range in levels of the design are given here in table. Then the equilibrium data were analyzed by commonly used adsorption isotherms and kinetic models. So after the leaching experiment and antibacterial test towards 2 different bacterial strains, the regeneration study was performed, as I already told, by non-thermal plasma operating at atmospheric pressure. The source was surface dielectric barrier discharge. So the saturated adsorbents with cyclohexene after the absorption was exposed to plasma for 20 minutes and then used again in the repeated absorption cycle as under the same condition as before to evaluate the regeneration efficiency. So the efficiency was tested through 5 absorption regeneration cycles, and the table in the middle gave the spent adsorbents that were regenerated and the clinoptilolite loading amount on it after the first absorption cycle. So I will continue with the results and discussion, but first I will go through the characterization of the prepared adsorbents. So the PXRD analysis showed that the crystallinity of clinoptilolite remained preserved after the modifications. So the characteristic peak of graphene oxide pattern is not visible in the graphene oxide modified samples due to the overlapping with clinoptilolite diffractions. On the other hand, 4 new diffraction peaks are visible in the patterns modified with magnetic nanoparticles, indicating the presence of new iron oxide phase. This can be either attributed to magnetite or macremite particles. So the surface morphology of the adsorbent of the magnetic clinoptilolite prepared was then analyzed by TEM analysis. And TEM analysis showed that both samples contain magnetite nanoparticles. Clinoptilolite modified by standard co-precipitation method show morphological degradation of clinoptilolite plate, while the clinoptilolite modified by microwave method contain less magnetite nanoparticles, and the clinoptilolite plates are less degraded. So the average chemical composition obtained by the EDS showed that the silicon to aluminum molar ratio of clinoptilolite changed by modifications. This indicates the partial dealumination of the clinoptilolite structure during the modifications. Further, the content of exchangeable cations in modified sample decrease, while the content of iron increase. And since the iron increase is much higher than the decrease of exchangeable cations, the modification with iron oxide particles possibly occur through not only iron exchange, but also precipitation of iron species on the clinoptilolite surface. So to determine the iron oxide phases present in the pure magnetic particles and magnetic clinoptilolite, both obtained by microwave-assisted method, was studied by the Moss-Bauer spectroscopy. So the results indicate that the dominant phase in both samples are macremite. But as we can see here on the first spectrum, the pure magnetic particles, in addition to macremite, contain a handful of different iron oxide phases, while the formation or iron oxide on clinoptilolite results only in formation of macremite. So the high resolution XPS analysis for the iron of magnetic clinoptilolite obtained by microwave show that the iron is present as iron 3+, which is in accordance with the Moss-Bauer results. On the other hand, the deconvoluted carbon peak shows 4 peaks binding energy listed here, which corresponds to the bonds that are also listed here and suggests the presence of oxidized graphene sheets on the clinoptilolite surface. So the thermal analysis show similar weight loss up to 300 degrees Celsius for all samples, which can be attributed to the loss of water in clinoptilolite cavities. At high temperatures, the loss differ from the modified samples and clinoptilolite. This can indicate for the transition of magnetite to maghemite for the magnetic clinoptilolites, and combustion of graphene oxide carbon skeleton at around 450 for the samples modified with graphene oxide. So the results of beta analysis showed that the specific surface area of clinoptilolite increased approximately 2 times after the modification with magnetic nanoparticles, as well as the total pore volume. On the other hand, the pore size diameter decreased for all modified samples. This can indicate the formation of second layer of magnetite nanoparticles on the clinoptilolite surface and partial blocking of the pore system by iron oxide formation. But on the other hand, the synergetic effects of magnetite nanoparticles and graphene oxide led to the increase of clinoptilolite surface area 3 times. So also to detect and confirm the graphene oxide on the clinoptilolite, the Raman spectroscopy was performed. Here's the spectrum of the commercial graphene oxide and the graphene oxide coated on clinoptilolite. It can be seen that the two main bands of graphene oxide are also visible in the spectrum of graphene oxide clinoptilolite, which confirm the graphene oxide on the clinoptilolite surface. Since, as I already said in the introduction, the cyprofloxacin molecule charge strongly depends on the pH, the surface charge of the adsorbents was also measured. So clinoptilolite has negatively surface charge over the entire range of pH values. The surface charge of clinoptilolite slightly changed with modifications for lower pH values, but it's still negatively charged in, let's say, wide range of pH. So also the magnetic properties of the synthesized samples was measured and compared with the magnetic properties of the pure magnetic particles. We can see that all samples show similar magnetic behavior, and the saturation magnetization value are listed here in table. What is important to point out here is that coating of magnetic nanoparticles induce magnetism to clinoptilolite, which doesn't have it by itself at the beginning, so that the separation of the synthesized or magnetic clinoptilolite is possible with external magnetic field from the solution after the adsorption. And another important thing is that magnetic clinoptilolites, both samples, retain the magnetic properties after the cyprofloxacin adsorption. So you can see this very profi video of magnetic separation. So it worked in the lab scale. Okay, further, the design of experiments enable the determination of the variables that have the most significant impact on the cyprofloxacin adsorption. So from that most significant parameters, the contour diagrams were obtained, and they enable the optimal conditions, the determination of optimal conditions for the adsorption of cyprofloxacin on every synthesized adsorbents. Then the three-dimensional surface plot were determined to see the interactive effects of initial concentration and pH for all three adsorbents at different temperatures and at a fixed contact time of 20 minutes. As we can see, the adsorption capacity was influenced by the initial concentration. The optimal pH is around 5, and the graphene oxide magnetic clinoptilolite show the best adsorption efficiency at all investigated temperatures. As for the kinetic results, the adsorption efficiency of all adsorbents increase with contact time, and we can see that in first that the adsorption is that the efficiency increase rather sharply in the first 5 minutes and achieve almost, let's say, around 85% of the maximum adsorption capacity, which indicate the fast adsorption. So the adsorption kinetic data obtained were then analyzed by 2 kinetic models, the Lagergren pseudo first and pseudo second order. The pseudo second order shows significantly better fits according to the linear correlation coefficient coefficients. So this is the reason why I will put these results here. And the rate constants change rather irregularly with temperature for all studied adsorbents. This phenomenon was also observed for cyprofloxacin adsorption on mineral clay and aluminum oxide, which indicate the complexity of cyprofloxacin adsorption mechanism. And the analysis of the results by Weber-Morris model show that the diffusion is not a rate-limiting step in the adsorption. So the adsorption isotherms in general show that the maximum adsorption capacity increased with increase in temperature. Since the increase for magnetic clinoptilolite composites is not so high, we can conclude that the magnetic nanoparticles did not influence the cyprofloxacin adsorption. On the other hand, coating of graphene oxide increase the clinoptilolite adsorption capacity for cyprofloxacin. The results of isotherm study was then analyzed by Langmuir and Freundlich isotherm. And according to the results, the Langmuir isotherm slightly better describe the adsorption of cyprofloxacin onto synthesized adsorbents. This indicates that the adsorption proceed to monolayer, that all the sites on the clinoptilolite are energetically homogeneous, and that there's no interaction between adjacent species of cyprofloxacin onto adsorbent surface. So the leaching experiments for 24 hours in sodium chloride solution show that only 20% of cyprofloxacin released from the pure clinoptilolite, by only 4% from the magnetic clinoptilolite. This indicates that magnetic coverage prevents cyprofloxacin leaching, and that the adsorption is mostly irreversible process. So let's say to use the adsorbent, the spent adsorbents as it is, the antibacterial activity test was investigated towards 1 gram negative and 1 gram positive bacteria. And according to the inhibition zone, both adsorbents, spent adsorbents, have high activity against both bacteria strains. This indicates the potential use of spent adsorbents in the tertiary stage of wastewater treatment process for water disinfection. Before I continue with the results of regeneration, first the plasma characterization was performed. So the electrical characterization or the electrical measurement shows stable plasma during these 20 minutes of treatment time. And to investigate the species that are present inside the plasma, the optical emission spectroscopy was used. As expected for air plasma, the most intense line in the spectrum was for nitrogen second positive system, then for nitrogen first negative systems, and there's also for OH radicals. So, pardon. I'm sorry, but for the according to the literature data, the species that are responsible for organic species of pollutants removal on plasma is this one listed here. And although they are not have emissions in the recorded range, they are present. I can say for ozone that it was there, so I could smell it a lot. So these are also species that are responsible and present in this plasma discharge. So first, the regeneration of the spent adsorbents with high clinoptilolite cyprofloxacin loading was performed. The high content means that I use the cyprofloxacin solution of 200 ppm for the adsorption. And as we can see, for the pure graphene oxide, we got the best results. So the removal efficiency remained practically constant during the 5 adsorption cycle, while for the other spent adsorbents, we can see that the removal efficiency gradually decreased with this regeneration cycles. So this can be related to the high cyprofloxacin content and then partially blocking the pore of adsorbents with the byproducts of plasma and cyprofloxacin. So then we reduced the concentration and the results was much better. So the removal efficiency with lower for the spent clinoptilolite with lower cyprofloxacin concentration show practically stable trend of constant removal efficiency. It degraded for maybe 10% in the 5th adsorption cycle, which indicate a good results. Then the characterization of regenerated clinoptilolite was performed to see if plasma had some impact on clinoptilolite structure. The PXRD results for the pure clinoptilolite and regenerated clinoptilolite after 1st and after 5th regeneration cycle showed that plasma didn't have any impact on clinoptilolite crystallinity. Also, the measurement of adsorption, desorption isotherm nitrogen showed that after the plasma treatment, the number of mesopores increased. And for the XPF depth profile of carbon, we can see that the loading clinoptilolite have, of course, the most the high amount of carbons, while it decreased after the plasma treatment. And we finally came to the conclusion. So in general, natural clinoptilolite can be used as an efficient and environmentally friendly adsorbent for the removal of antibiotic from pure water. As for the prepared adsorbents, the magnetic nanoparticles coating induce magnetism to clinoptilolite, and the graphene oxide coating increase the specific surface area. The adsorption experiments show that the adsorption capacity increased with the increase in initial cyprofloxacin concentration, and the optimal pH is around 5. More than 80% of the maximum adsorption capacity was achieved within the first 10 minutes, which indicate the fast adsorption. The adsorption process followed the Langmuir isotherm model and can be described by the pseudo-second order kinetic model. And also the adsorption mechanisms most probably include electrostatic interaction and ion exchange reaction. So the leaching and antibacterial tests show that the magnetite pouch prevents clinoptilolite for leaching, and that there is a possibility to use the spent adsorbents in the disinfection of water. And also the reusability test showed high rate of regeneration and say that actually plasma is a potential in a good innovative and novel treatment for regeneration of spent clinoptilolites. Thank you. So I would like to acknowledge everyone who worked directly and indirectly with me at the Novelties project. And also thank you to my supervisors, Professor Nevin Karajic and Professor Lidija Čurković, but also to my colleagues at TMF at the Department of General and Inorganic Chemistry, and also all the professors and colleagues that worked with me in Zagreb at FSB. Many thanks to the Center of Non-Equilibrium Processes at Institute of Physics in Belgrade, where I worked the plasma part under supervision of Dr. Nikola Škora. I would like to acknowledge the colleagues from the Jožef Stefan Institute in Ljubljana and Professor Vilko Mandić for the analysis. And finally, my family and friends for being with me all the time, no matter what. So thank you, Maya.
For a very clear and very efficient and nice presentation of your work. Now we will go to the part with the questions. So first I would ask Professor Novak Tusher to make the question.
Yeah, thank you very much for really very nice presentation, very clear, very structured. So really congratulations for this. So actually your work, so you showed us also this, that it was very complex. So you considered all the parameters for your study, and you also stated in your work that you designed a low-cost adsorbent. And this is true. But, and also the added value of this work is the treatment of the regeneration, or to design the regeneration of the adsorbents with the innovative methods. So I wonder if maybe you think about also to evaluate the economic justification of this innovative regeneration treatment, because this could also bring some costs,
of course,
if you think about the scaling up of the process.
Yeah, actually, if I may, actually, the main, let's say, problem with plasma is the scaling up. So to obtain that, you can treat a higher surface or volume at the same time. So this is very low surface area. We actually performed the let's say some little scale up, but it was, from this to this, and it was good. But in general, not just this type of source and type of plasma, they all have like a problems with scaling up, and so to use it in some, let's say, industrial scale. So yes, I thought maybe I would have time to make some, economical analysis out of this, but in the end I didn't. So yeah, but that's a good question and comment.
Yeah, that you can do for the future, no?
I mean, the light is, it's very cheap, so you can just. I asked once my colleagues. So I always say that it's economically feasible. It's very cheap. But can you tell me, like, the price of this bed that you got? Or just something to go. That was the answer. So, yeah, that's a good potential, like the adsorbent. But there's also in this in this research, there's also, so first you need to synthesize, to purify this clinoptilolide, and to synthesize it, possibly by microelasticity, which is economically more feasible and energetically. And then you need to regenerate it. So yeah, there's a lot of gap that still need to be filled, let's say.
Yeah, but it's already, regeneration is really, I think, added value. So yes, it's nice.
Yeah, this is, I think, the most novel thing in my work that I'm proud of.
Yes.
Still, I don't know how to scale it up, but I think that all the the scientists that are working with plasma are struggling with that. So maybe it will be some good results regarding scaling up in the future.
Yeah, the good direction. Okay. And the second question, now you used only a model pollutant of one of the pollutants group for,
Yes.
for water. So what do you think for the future? Which group of the pollutants could be the next one? Because if you want to use this in the real wastewater, then you need to test actually more pollutants groups.
Yeah, but I mean, I need to test, like, to use a complex matrix for the beginning, or just take a head water or wastewater, and then spike, for example, cyclofluoxetine in it. I know, and that's, I don't think that it will be so simple then. Now it seems like, oh, it's perfectly, it will move very well, but I think that this is also one parameter that need to be investigated in the future. Yes, so I agree.
Thank you very much.
Thank you.
Thank you. And next is Professor Mandic. Professor, if you can address a question to our candidate.
Yeah, I hope you can hear me, so we can move on with that.
Just one. Okay, can you try now?
I can repeat. Can you hear me?
Yes.
Yes.
Okay. Again, now it's a little bit difficult for me to hear because of the echo, but I'm just gonna say the questions and hopefully you can discuss a little bit about that. So in terms of determining or basically analyzing crystal phases, that is, let's say, in most of the cases, straightforward thing, but not maybe in the cases when there is, let's say, the similar level of structural ordering between the phases, but let's say different chemical compositions. So how do you move forward from that, let's say, challenge? Do you have any ideas? I mean, you did it, but I would like to discuss a little bit about the strategies, how to do that. And well, that's the first one, and then we can discuss the second one.
Sorry, you mean to how to distinguish, for example, here I worked with magnetite and macamite.
Yeah, let's say you have a similar phases from the structural point of view, but they are obviously different phases from the compositional point of view. So their diffractograms would kind of be very similar. And then you are faced with the question, is this which of the phases is which? So how to move forward from that challenge? Just say, okay, I probably this is like that, or you have additional tools to
depends on for example, this iron oxide particles, I use Mossbauer spectroscopy, and I think this is like the most the good method for recognizing is it a magnetite or macamite. But I think that also XPS can be used, since the XPS also showed that there is a iron in 3+, which means macamite in my case.
To the point, yes, but in terms of, let's say, just from diffraction data, so if you just have one device, what would you do? How would you additionally analyze the results?
Maybe the reference intensity ratio method from the diffractogram.
Okay, and how would that help you?
To see which phase, because, for example, in my case, magnetite and macamite have similar structure, but have some defects that you can analyze and see the differences. So maybe according to this RD peaks surface, there's some different parameters for the macamite and magnetite.
Yeah, of course, there are
the same diffractions in the X-rays.
That is basically what I wanted to hear. So you have let's say a whole level of additional information available in the just simple diffraction package, and using the databases, you can really reach down to well, not gathering only qualitative but also and quantitative information. Other than that, maybe can you comment on the, let's say, shape of the signal during the characterization of plasma? So that is kind of a mysterious thing for me. You can also find it in your presentation.
Okay, I understood well. Just a minute. Maybe I can show it here. Oh,
Yeah,
this one, you
exactly.
think,
Yeah,
like the current in time.
current time, voltage time.
So this type of plasma contains some, let's say, micro discharge. So plasma, let's say it's a plasma discharge, and there's a micro discharge in the plasma, and you can see it in the picture here. So the plasma is not homogeneous. That's the point. And because it's not homogeneous, it's not a sinusoidal, like it's just, let's say, peaks. It's due to this micro discharge filaments that occur during high voltage and low current.
Okay, so basically you are using the shape of or phenomenology of the shape of the curves to basically distinguish what type of plasma or what state of the homogeneity of a plasma you have at that point, something like that.
Yes, because it's also surface dielectric barrier discharge, which means that have this dielectric, which was glass in my case, to actually reduce the energy of the high energy electrons that occur in that kind of plasma when you actually, let's say, discharge or ionize the gas, because you need high voltage to ionize the air. And then you have this glass that actually prevents the formation of arc plasma, which is very destructive plasma and strong.
I'm fully satisfied with the answer.
Thank you.
Thank you, Professor Mamic. So we now move on. Professor Simon, it's your turn.
Okay, thank you, colleague Skoro. Barbara, that was a nice presentation. And there is a whole lot of research in your doctorate. So I would like to point out some things and ask you. Regarding the model, can you tell us something about the relative effects of the included factors? Which has the most influence on the ciprofloxacin removal, and what can you say, what is the optimal setting for removal of the ciprofloxacin?
So the most significant variables of cyclofloxacin absorption is first the initial concentration of cyclofloxacin, then the pH, then the type of adsorbent, and then this is a linear parameters, and then the combination of initial pH, temperature, and the adsorbent type, which is also shown here. So what can we see from this plot is that the adsorption capacity strongly increased with the initial cyclofloxacin concentration, and that it also decreased with from changing of pH from 5 to 9. So that in this case, for the study studying of this range, the optimal pH found to be 5, around 5. So the best absorption capacity was achieved for the graphene oxide magnetite, which I can see here also according to colors. And that can be attributed to this graphene oxide quoted on, because graphene oxide significantly increase the specific surface area.
Yes, yes. Thank you. Another question, just a little bit. You can control the factors pH, but you can't control initial concentration. Initial concentration is something that you get from the contaminated water. Yes. Okay.
Yes.
Okay. So firstly, you measure the concentration, and then you find the optimal parameters such as pH and let me say others that
Yes,
you
I
mentioned.
actually said the initial concentration, but to let's say to maybe measure some efficiency of the process, maybe it's important to have like the initial concentration and then final concentration, then just to to optimize the process better.
Okay. Yeah. Thank you very much.
Thank you.
Thank you very much. So, Professor Dubach, it's your turn.
Thank you, Nicola. Barbara, thank you again for your really nice presentation. I would ask you two questions. So let's repeat. For the modification of cleanup phthalate, you used the conventional method of precipitation and microwave assisted synthesis. And can you please compare both methods regarding the obtained properties of the material, similarities and differences?
Okay, so according, let's say, to chem analysis, I didn't put it here, but because of time limitation, but the magnetic cleanup phthalate obtained by standard co-precipitation results in formation of magnetite nanoparticles. Because I use like nitrogen atmosphere, so there's no oxygen, so it is let's say better controlled from my side. And so the formation on obtained by conventional is magnetite, while in a microwave assisted method, in addition to magnetite, and further I realized that there's also a macremite, there's Getat needles, which is iron hydroxide needles. This so the magnetite have among these iron phases, magnetite have the best magnetic properties. So if I have more other iron oxide phases, the magnetic properties of the sample decrease. So it's lower. That's, I think, the main differences according to the synthesis. So here in microwave assisted, you can get also like this hematite and macremite and different oxidases. While here for the co-precipitation method, I detected only magnetite.
Okay, thank you. And second question, could you compare the absorption capacity of ciprofloxacin removal using modified zeolite for both methods?
There's no significant change or differences, I would say. So as we can see here, both magnetic cleanup phthalate have practically the same absorption capacity for all the investigated samples. Temperatures and initial concentration, sorry.
Thank you very much.
So it's only on the, let's say, some surface morphology and what species will you obtain, and the species will affect the not also the surface, the absorption capacity, but just these magnetic properties.
Okay, thank you.
Thank you. So,
First of all, I have to say it's a great pleasure to be a member of this committee. I met, I think, 3 years ago, that guy. And I was also the member of the committee for the final doctoral exam. So she distinguished herself as a very intelligent, hardworking, and very polite person. So I respected more than that. I was sure it will be an excellent doctoral dissertation we are facing it now. And also my colleague, Professor Nevenka, confirms all my expressions about Barbara. Barbara, my field of expertise is water treatment, as you know. So please, can you tell me what is the reason that I should choose your novel absorbent instead of well-known, very proven activity retardant? What are advantages and disadvantages of your absorbent comparing with activity retardant?
First, I think it's cheaper than activated carbon. Also, the absorption of some species, according to the literature that I read and went through, that the absorption is faster from some, yes, faster. So for the regeneration, I think it's mostly depend on what kind of species do you have. That's actually a problem, not the advantages. But what kind of species do you have in water? Plus, in addition to the pollutant that you want to remove. So also the cleanup to the zeolite, let's say it's not selected, so it will absorb different species from, not just the selected ones. So maybe it's also an advantage.
Okay, thank you. And as Professor Lydia ordered, asking me to be very brief, on 2 questions, not more, and no, not too long. The second question is, can you tell us something more in detail about what I'm interested in, and that's how do you propose to use a spent or exhausted absorbent as the lubricant for water treatment? It's very interesting for us who are dealing with water treatment. Can you explain us that idea?
So, since the results showed that if you use this magnetic film of zeolite, that the ciprofloxacin will practically stay on it, only the 4-5, let's say, % will leach out. So you can put it in the water, maybe in some pool for treatment, and mix with the water, and then remove it by magnetite. Let's say, I'm not sure about how to use magnetite in a big scale, but these tent absorbents will retain the antibiotic on it and practically remove the bacteria from the water. Okay. Yeah, I'm not sure. So here we need to point out that the amount of adsorbent and the water is also important to to optimize, let's say.
So, very interesting for next research.
Let's say, yes. I also need to see how these microorganisms act. So I can say if they just removed or killed, or maybe in one part of the pool, so just removed. I'm not sure about that part, but
Thank you.
Thank you, Dr. Jones.
Thank you. First of all, I would like to thank Professor Reich and Professor Churkovic for the opportunity to be a member of this PhD Defense Committee. And thank you, dear Barbara. This was truly, truly effective, and I genuinely enjoyed your presentation today.
Thank you.
Not more than I also enjoyed reading your written work. It is very well structured, very decently written, so all compliments goes to this. You presented today a really huge amount of experimental data. So I'm completely aware how much time and dedication you have committed to this work, starting from material preparation, functionalization or modification, also techniques for various characterizations and multi-cycle absorption, leaching, antibacterial tests, etc. So can you tell me what was the most challenging part in terms of experiments for you? Because I'm sure that you had to go deep inside of all of these approaches and techniques, including also modeling and experimental design, etc.
Okay, let's say that I enjoyed in optimization of the absorption process at the beginning, because I put some amount of cyclophosphamide solution and the zeolite, and it just go like in 5 minutes. So what next? So the optimization of absorption was challenging. Then also the regeneration, when I established, okay, I tried to leaching to ion to make the ion exchange of this. So then to see how this antibiotic actually attached or absorbed on, and then the regeneration part, because first I said, okay, I can use plasma for activate the zeolite surface according to the literature data that I read. So maybe I can improve the absorption. And then I said, okay, but we also need to regenerate it. And then together with the colleagues, they said, okay, and professors, let's regenerate it. So that was, I think, the most exciting part for me. And as I already said, that my research had novelty in this regeneration part. Yes.
In particular, I really like this part of regeneration. Especially that means that you close the loop of material usage, which is the tendency of today, of course. And speaking about all these results, I've noticed that you published 3 scientific papers, among which is applied surface science, one of the most prestige in the field of applied chemistry and materials as well.
That was beautiful.
Okay, okay. Perfect. And my last question will be related to this potential tertiary treatment. You have tested antibacterial, maybe also, no, it's okay, it's just a question about, would you consider to test to antifungi treatment like Candida albicans or something?
Yes. It would be a good idea.
Yeah. Thank you very much. It was truly splendid.
Thank you very much.
Thank you. And now it's my turn. So before I ask one question, I really want to congratulate first to the clear presentation of all the results, and there's all the committee members also noticed there are so many different, let's say, elements or parts coming from different scientific fields. So this was very hard. I guess it's not very easy to put them all together and to present them in a compact way. Of course, the thesis is really nicely written with the many explanations, and for the research in the background, it's also nice. So really enjoyed the collaboration with you, and I think also other colleagues, not only from this physics, but also from this project. that they also enjoyed working with you. And I think we got all of us the project and the mentors of the thesis and all researchers that were included. We all got a lot of different knowledge that we didn't know, like from the beginning. For us, this material part was something new, and for you it was plasma and the physics, and yeah. So I think it was a very nice combination. Eventually, we also got very nice and promising results. I have one question, and it's related. As we could see, this is quite process. The regeneration, plasma regeneration process is something that is that can be really technologically applied for really treatments and the generation of zeolite in the future, maybe for bigger scales. So since this zeolite is used, the sorbent is used in water and then regenerated by plasma. So actually the sorbent comes from the water, it's taken out from the water, so there is some humidity in it. So what would be the influence of this humidity of the zeolite sample on the plasma treatment that you perform?
Okay, first I dry it in so absorption, then drying, then plasma, but still, since it is zeolite, there is moisture in the air. So yes, the content of water or moisture in the sample can affect the, let's say, plasma chemistry, because when plasma comes in contact with water molecules, novel oxygen and nitrogen species were formed that can, let's say, make more richer environment, plasma environment, and then help to degrade or clean the zeolite surface. So I don't know the exact influence in my case, because of course there is a moisture, there is a water in the zeolite. Plasma can interact with the water molecules, okay, only on the surface, let's say atmospherically absorbed. But there's also humidity in the air, and I use air. So yes, the water in the sample can contribute to formation of more these species, which can help, let's say, to clean the zeolite surface,
So actually,
to make a richer, yes.
More humidity in some case could be even beneficial for
Yes,
the
yes. Maybe I can put like from water to plasma, but I didn't try this. Okay.
Okay. Okay, thank you.
Thank you.
Da li sad imam samo pitanje, da li neko iz publike u sali ima da postavi pitanje
Može i komentar.
ili komentar?
Možda pohvala.
Evo.
Ako nema, onda će se komisija
Ja ću iskoristiti ovu priliku, ako mi dozvolite, samo nekoliko rečenica, mislim da ih možda neće biti na kraju. Ja bih zaista želela da se zahvalim svim kolegama koji su učestvovali u evaluaciji i u oceni ove doktorske teze. Bili su vrlo ekspeditivni, mnogo su nam pomogli i bez njih ova teza verovatno ne bi bila ovako uspešna kako mi se čini danas da jeste. Želela bih takođe da se posebno zahvalim ovom kandidatu. Bilo je zadovoljstvo raditi Barbara s tobom, bilo je zadovoljstvo gledati kako sazrevaš u tom istraživačkom procesu ovde. Želela bih da zahvalim njenoj mami koja je ovde, koja ju je tako lepo odgojila i sa kojom zaista može i danas, nadam se u buduće da se ponosi. Eto toliko i svima bih želela da zahvalim što ste bili gosti Tehnološko-metalurškog fakulteta. Hvala vam svima.
Hvala profesorice.
So now the committee will go out for the decision, and those who are following us over YouTube, please stay for the final decision.
Okay.
Okay, so I will first speak in English just shortly because this procedure is took quite long time. Double degree also means double administration for the degree. So in any case, the administration was too long, but our decision and the consultations were very short. And as you could hear, the whole committee was with one vote that Barbara defended her thesis named Surface Modification and Functionalization of Natural Zeolite, Clinoptilolite, and she was awarded degree PhD that we also the committee decided to rate the dissertation with the highest degree summa cum laude. Samo ću sada kratko pročitati. Dakle, posle javne odbrane komisija je razmotrila izlaganje i odgovore i odbranu disertacije i jednoglasno donela odluku da je Barbara Kalebić, magistar inženjerka ekoinženjerstva, odbranila svoju doktorsku disertaciju pod nazivom Surface Modification and Functionalization of Natural Zeolite Clinoptilolite i time je stekla pravo na promociju u naučni stepen doktor nauka, inženjerstvo zaštite životne sredine, odnosno doktoricu znanosti iz područja tehničkih znanosti znanstveno polje strojarstva. Dakle, komisija je jednoglasno takođe odlučila da se za tezu dodeli najviša ocena summa cum laude. Ovom prilikom čestitam Barbara na odbrani.
Hvala vam. Evo,
Hvala.